Hello, I am Hunter Wilson, and this is my tutorial on how to do a 2D Fluent analysis on a nozzle. So you begin by using this Fluent schematic, and you need to start with your geometry. I have it pulled up here. I used a MathCAD code to get the plots of this 80% bell nozzle curve, and then you add straight lines to this axis and complete this body. I used half the nozzle because you can use a symmetry relation later on to get the rest of your information. So after you create your geometry, you need to go to your mesh. Here's my mesh for my 2D nozzle. In my mesh, I began by generating a simple mesh that didn't look very good. So I used a face mesh in order to clean it up and make it cleaner. Then I went down to my sizing and used adaptive sizing and increased the resolution in order to create smaller elements. I then used a refinement mesh to make the elements even smaller, and you can see that here, and I used one refinement. I also used, let's see, it was quadrilateral, yes, mesh. Then once you have your mesh here, which the elements, my elements number was 54,216. From here, you want to name your selections parts of your geometry. I have the inlet on this side, the outlet on the other, the wall, and the center line called symmetry. From here, you can go back to your setup and start in your initialization. So here I have already completed it, and you start by going to your models. You need to turn energy on. You need to go to your viscosity, edit that, and make sure it is inviscid. Then from there, you go down to your materials and make sure your air is selected. It's pulling up. It is an ideal gas. You change, close, and then you go down to your boundary conditions. From here, this is where you assign your geometry. For your inlet, you have to make sure it's a pressure inlet, and you need to change its boundary conditions. Here I have changed my total pressure to the stagnation pressure of 9,700,000 Pascal, and also changed my initial gauge pressure, which I calculated using interpolation from our isentropic tables for our given aspect ratio of 16. This is the subsonic initial pressure. You also change your total temperature to our stagnation pressure of 3,710 Kelvin. You apply those. Then you need to go to your outlet and you calculate our outlet pressure, which is our exit pressure, to be this, using our isentropic tables, as well as find your exit temperature to be this. Then that's all we need for our boundary conditions. You then need to go down to your initialization, and I used a hybrid initialization. Current data has not been saved. I have already run this. So once you click initialize, you can then go to your run calculation. Here I used 1,000 iterations, and it did converge before then. You can see here down here are my contours, and I set up each contour, display. Here's my speed of sound. For my report that I did, you can go up to your view, and if you want the whole nozzle, you can simply click on your symmetry and apply, so you can understand what's going on throughout the whole nozzle. And here is each of my contours. If you want to create more, you can go up to results, contours, new, and simply enter the data that you want to identify. Again, here's my velocity. Density looks good, is decreasing. My temperature also, it should be hot as it goes through the throat and cools down. And here's my pressure. Right here. Okay, and then you go to your XY plots, and this is where you can create multiple. I created XY plots for pressure, temperature, density, velocity, Mach number, and speed of sound. When you get here, you can name your plot, and then identify which axes you want the plot to view. And this is where your center line comes in handy, because you want to know the data along that line in the center of the nozzle. So you can save and plot. Here's my data. In my report, I imported this data by using the write to file function and imported that into Excel, where I combined the data between my bell nozzle and my conical nozzle and overlaid the data and create those curves. So here's all those curves. I will repeat this once again for my conical nozzle, because there is a little bit different. So for the conical nozzle, it initially begins, I do not have this pulled up already, so forgive me, just give me a moment for it to load. My computer is kind of slow, so just be a little bit patient. You know what, I am also going to, oh, maybe I don't have to close my current stuff that is open. So this is my conical nozzle as it opens. You create this geometry by using the same, very similar MathCAD bell nozzle. However, when you import the data and you draw those lines in the geometry, you can just simply connect the exit to the throat and the throat to the inlet, and you will keep the aspect ratio the same between the exit and the throat. Okay, so once I had that, I went ahead and imported that into the mesh. So we'll go here. Again, this is going to take a moment to upload. This project was very exciting. I think it was very challenging to get the mesh correct, because depending on how many elements you have, you can change your answers, and definitely spent a lot of time trying to figure out just the right mesh, having not used this before. Okay, so here we go. Here's my mesh for the conical nozzle. Again, physics, CFD, solver, we're going to be using Fluent. Element size, I left it alone. Sizing, again, I used adaptive sizing and an increased resolution. And in my mesh, you can see I once again did the face meshing to make it neat and cleaner. Again, I used a refinement of 3 to decrease the size of the elements, therefore getting more elements. Again, this is where you assign your geometry, your inlet, outlet, wall, and your center line. Once you have this, you can go ahead and go into your setup. Close. Let me close out of this, because I believe this is the bell nozzle. Okay, it's just saving everything. Okay, I think it is almost done. I found that using 1,000 iterations, my process and calculation actually converged before I completed 1,000. I think for the bell nozzle, it took more. I know the bell nozzle took more iterations than the conical nozzle, but they did converge nicely. Okay, so I'm picking up right where I left off. I was creating the setup for the conical nozzle. You need to make sure you click double precision, click start, and it will take a minute to load. Okay, we can see it here, it is opening. Still importing the mesh. Okay, it looks like it is almost done. Okay, so for this mesh, this is my conical nozzle. You need to make sure your type is density based. Again, go into models, you need to make sure energy equation is on, it is inviscid. Same things, fluid, air needs to be an ideal gas. Again, for your boundary conditions, you set the same boundary conditions. I'll give an example. See my inlet here, my total pressure is again the same. Same with the pressure. I believe the outlet is also the same. Now you need to go down to initialization, hybrid, and initialize. We'll run through the whole calculation for this one. You can see the hybrid initialization is done at the bottom. Let's do 1,000 iterations. Let's check case just to make sure there's no errors. Okay, everything looks good here. Close and calculate. So while we wait for this to calculate, you can see your number of iterations on the side, and then the prediction for how long it is going to take on the right, second to left, and how many iterations are left here. So what we want is for our calculation to converge. Again here, I think we need to remember that the mesh was very important for this process, and I increased the amount of elements for one of my trials, and it was around 200 something thousand elements, and it actually did not converge, and it did not look very good. So I needed to redo the mesh, and it was through watching tutorials and various YouTube videos that I found what I believe worked best for my case. This is going to take just a little while because my computer is not the fastest. So we see here it's already at 27%. I do not think it will require the whole 100%, all 1,000 iterations to converge. Should converge before then. Now it's interesting to think about whether your results will be the same as the bell nozzle, because the expansion ratio is the same, and we set the same pressure for the inlet and temperature as well as for the exit. However, we will find out that our values are not actually the same, and we find out that our bell nozzle exit Mach number is actually higher than our conical nozzle exit Mach number, which is actually a desirable result, and more of that will be discussed in my results. So let's see, is that 50%? Hopefully not much longer. You can also select the amount of cores you want your computer to use while running these calculations. Increasing that does help with how fast this goes. Alright, good. It looks like it has gone ahead and converged. There we go, at only 656 iterations. And we can see here all of our plots and contours being generated. So we can go down to our graphics, contours. Again, look at all of these. Here's my Mach number. Okay. And again, you can go through all of these and look at your min and max values, and it's also interesting to look at how your geometry affects the internal elements and variables. These graphs and contours are very nice to look at. They're very pretty, and they do all make sense. Again, here's my XY plots. Save plot, speed of sound. There we go, speed of sound is decreasing as it should. Velocity increasing. Density. There we go. You can change your plots here. Save and plot. Here's my density. Temperature also decreases. Pressure should also decrease. There we go. Thank you for watching.